Hello, everyone. Welcome back to this week's algebraic graph series seminar. And happy Chinese New Year. And today we have Steve Butler to tell us some cool things about the Hadamard diagonalizable graphs of small order.
All right, well, I guess Chinese New Year, Xinnian Kuai La, as they might say. So thanks for coming. So we're going to be, as was said, Hadamard diagonalizable graphs of small order. Now, small, we'll get to what that means. And this is a group project, and you can see a lot of people worked on this. And some people might be familiar with some of these people. Jane Breen works at Ontario Tech, not too far away from Waterloo. Melissa Fuentes, Bernard Lidický, Michael Phillips, Alex Riasanovksy, Xiaohong, Ralihe, Villagrán, Cedar, Wiseman, and Xiaohong, Zhang. Well, let's get going. So, there we go. Now, this grew out of a research problem that was part of the 2019 Graduate Research Workshop in Combinatorics. Now, for those not familiar, this is a 2-week workshop where we bring together lots of graduate students, some postdocs, a few faculty, and work on problems. It's kind of familiar with REUs, like REUs for graduate students. And part of the process is when people apply, they have to pose a problem. So Xiaohong Zhang applied. And her problem was the following. It says, let's characterize Hadamard diagonalizable graphs of order 16, 20, and 24. Okay, and well, why those? Well, prior to this, it had been known up to 12. So for Hadamard matrices of order 12, what kind of graphs are Hadamard diagonalizable? And we'll get into what the definition there is. So 16, 20, 24, okay, that's sort of the next logical step. And the good news is we succeeded. And not just there, we actually pushed it a little bit past that as well. All right. Well, so now let's get into some of our basic ideas. So recall a Hadamard matrix. It's a ±1 matrix, which has the following property. If you multiply the matrix times its transposed, you get n times the identity. In other words, you can think of it as a ±1 matrix with orthogonal columns. All right, well, there's a very simple example, 4 by 4. And well, what can you do? There's a couple of things. One is you can take Hadamard matrices and make bigger Hadamard matrices. So Sylvester had a nice construction. I said, suppose you start with just a simple Hadamard matrix. You can actually start with just a 1 by 1 matrix, which is 1, and then you can build it up, double its dimensions, where you do it, where it says H, H, H minus H. And of course, you can keep going. So now you have all the powers of 2. All right, well, what about non-powers of 2? Now, what was known is there were constructions that were found. For example, Hadamard found a construction. And so you have other orders, 12, 20, and so forth and so on. And so there's a lot of matrices which are known. And of course, there's a lot that we don't know. So for example, we don't know if there's a Hadamard matrix of order 668. All right, well, maybe. But that's not what we're going to get into. So what we will talk about is the following, which is, what does it mean to be Hadamard diagonalizable? So a graph G is said to be Hadamard diagonalizable if the columns of the Hadamard matrix can be its eigenvectors. Okay, well, another way to say it is there's a Hadamard matrix. So H star times the Laplacian matrix L times H is a diagonal matrix. And recall the Laplacian matrix of a graph, that's the matrix which has the degrees on the diagonal, and then the off diagonals are 0 for non-edges, -1 for edges. All right, so that's Hadamard diagonalizable. Now, well, what can we say? So there's a few things that are known. So Barik, Follett, and Kirkland, they were able to show Hadamard diagonalizable graphs are regular. And moreover, all the eigenvalues are even. So they're even integers. Okay, so they're very nice from a spectral standpoint, but of course we can say a little bit more. So another work, Johnson, Kirkland, Plosker, Story, and Zhang said, okay, let's look at that Sylvester construction, a really nice construction where you can sort of build up powers of 2. And it turns out that what you get are the Cayley graphs. So the Cayley graphs are all the Hadamard diagonalizable ones for the Sylvester construction. So now for that particular Hadamard matrix, all right, that's everything. Okay, so we know what's Hadamard diagonalizable by the Sylvester construction. Another way to think about it is we also have this nice class of graphs, and the Cayley graph for Z2 to the D. All right, that has to be Hadamard diagonalizable. And one other observation, and it's the following. Suppose you have a Hadamard matrix of order n, and any Hadamard matrix of order n, then you can always use that matrix for the eigenvectors for the graphs Kn, Nk1, so Kn being the complete graph, Nk1, n isolated vertices, the complete bipartite graph, Kn over 2, Kn over 2, and 2 times Kn over 2. All right, so those 4 matrices, those 4 graphs are always Hadamard diagonalizable for any Hadamard matrix. All right, so in some sense, that's what we know. At least that's what we knew. And so what do we want to do? Well, we want to start doing more. So for instance, say order 12 is known. That was a theorem, and it's non-trivial. Took a couple pages. We'll come back and visit that. Let's say, what about order 16? Because there's many Hadamard matrices, and for order 16, the Sylvester construction is just one. Maybe there's other Hadamard matrices that give you other graphs. And so we want to say, okay, what can we do? So there's some approaches. So the first approach I call the hopeless approach, which says, okay, go through all the graphs. All right, there's a lot of those. All right, now just pick out the ones where all those eigenvalues are even, because we know they have to be. All right. And then even once we found that, we're not done, because we have to figure out, well, what can we say about their eigenspaces? Can they always be represented by combinations of these nice ±1 perpendicular vectors? That's not so easy. And so that's why I say hopeless. Okay, all right. Well, so we're not going to do that. So that says start with the graphs, try to find a matrix. We're not going to do that. We're going to do it a little bit differently. Let's start with the matrix. We have Hadamard matrices for small orders and say, okay, well, what do we have? Well, those are our eigenvectors. Okay, great. Now, what about the eigenvalues? Well, we know they have to be even, and they can't be too large. There's really essentially just n possibilities. And so that gives you roughly n to the n. Okay, that's not great, it's super exponential, but it's mildly hopeful, not too bad. We want to do, though, a little better. So what we're going to do is go through our Hadamard matrices, but we're not going to do it where we're going to test all possible eigenvalues, because that's, like I said, n to the n. We want to knock it down to just exponential. And well, it says be clever. It's not super clever, mildly clever. We don't need a huge idea, just need one good idea to get going. All right, so to recap where we're at. So if you look here, we have Hadamard matrices is in the column with matrices, and that's how many are known. And so up through order 32, we know exactly how many Hadamard matrices there are. 36, we don't know. And you'll notice there's a big jump at 32. So there's a lot of Hadamard matrices that exist. And then in the other column where it says graphs, those are Hadamard diagonalizable graphs. All right. Now, where do you see the 4s? Well, that says, well, we always know there's 4 graphs that always have to be Hadamard diagonalizable. So as soon as there's a matrix, we have 4. All right. And then the 46 and the 1372, well, those are our Cayley graphs because we have that Sylvester construction and we know that. All right, so that's what we knew before. And here's the result. There's the actual values. Okay, so for 16, we can jump back a second. It was at, say, look, we had 46, we're at 50. So there's 4 more that fall outside of the Sylvester construction that can be diagonalized. And at 24, well, we were at 4 and we jumped up to 26. Okay, so there's a lot there. And on 32, well, we went from 1,300 to over 10,000. All right, but you're probably noticing, wait a second, there's a lot of 4s here. You might notice that in fact, every other number on this list is a 4. All right, well, that's suspicious. That we need to do something about. And you'll notice, well, it's good that it's a 4 for 36 because our approach where we start with matrices, we can't do exhaustively because we don't have all the Hadamard matrices for order 36. Okay, so now our theory. Why is it when we look at the numbers n equals 4, 12, 20, and so forth and so on, there's exactly 4. So we know there has to be at least 4, so we just need to argue why are there exactly 4. All right, so here we go, a theorem. So for n equals 8k plus 4, the only connected graphs which are Hadamard diagonalizable are the complete graph and the complete bipartite graph. Now, some quick facts, we just pause. Why does this finish it for us? Well, now we just say, look, if something's Hadamard diagonalizable, so is the complement, because there's some very nice properties about the Laplacian and its complement. And so a graph or its complement is connected, so we just need to figure out what's possible. All right, so the nice thing is we can fit the whole proof into one slide. So I consider this the book proof of this result. And it's a really, really beautiful proof. My co-authors came up with it. This was not by me, but my co-author, brilliant co-authors there. Okay, so let's begin. And of course, as always, we have to have the disclaimer. Every talk should include one proof. So this is our proof. The rest of the talk will be more sort of algorithms and computational results. But here's our proof. Okay, so our first thing is let's assume that our regular connected graph is not the complete graph or the complete bipartite graph. Okay, that's a reasonable assumption because we already know that those are Hadamard diagonalizable. Now the claim is that somewhere in this graph, there has to be a path on 4 vertices that does not finish to a cycle. So when you look at the diagram, you see that X is connected to W, W is connected to V, V is connected to U, but U and X are not connected. Now, we don't care how U and W, whether they're connected or not. We don't care X, V, whether they're connected or not. Simply, again, we have a path on 4 vertices that does not complete to a cycle on 4 vertices. So how do we know there's such a thing? Well, let's look at the girth. Suppose the girth is 5. Okay, if girth is 5, we're done because there's a pentagon. Just grab a path on 4 on that. Okay, no problem. What if we have girth 4? Well, if girth 4, that says we have at least a K22 somewhere. Okay, so now take the largest complete bipartite graph you have. It's something KPQ. It can't be everything because otherwise, if it's everything, it's K n over 2 n over 2. So there's some vertex that connects to that graph, and it can't connect to a whole side. And now once you have that vertex that can't connect to that whole side, then you can find that path. All right, so that's girth 4. What about girth 3? Okay, well, take a triangle. Because there has to be a triangle. And now pick, oh, is there a question? No? Okay, all right, take a triangle and now take any vertex because it has to be adjacent to something. So take a vertex that's adjacent to something in that triangle. If it's not adjacent to everything in that triangle, we're done, because we can find such a path. So it has to be adjacent to everything in that triangle. So now we have a little K4. Okay, now take another vertex that's adjacent to something in that K4. If it's not adjacent to everything, again, we have a path. So it must be adjacent to everything, and you keep going, and you end up either you find that path or you end up with a complete graph. Okay, so that's the hard part of the proof. Now, the rest of the proof. So we have our nice graph. We know that there's a path, and we know it's Hadamard diagonalizable. Okay, so we start with our Hadamard matrix. We'll let H sub k be the column, the kth column. And because it's Hadamard diagonalizable, well, that says that our Laplacian matrix looks like 1 over n times the Hadamard times the eigenvalues times the transpose of the Hadamard. Okay. And if you work it out, that's 1 over n, the sum of the eigenvalues lambda k times hk star. So essentially, we're just doing a projection matrix. Now, take the ij entry. And the other thing is multiply both sides by n. So n times the ij entry of our Laplacian matrix looks like the sum over all k, lambda k, and then the ith entry of the kth column times the jth entry of the kth column. All right. Now, how do we use this? Well, we're going to do the following. We're going to take 4 entries of the Laplacian matrix and add them together. Now, remember that we mentioned before, an edge corresponds to -1, a non-edge corresponds to 0. So for instance, the Laplacian matrix UV, there's an edge, that's a -1. Laplacian matrix for UX, non-edge, that's a 0. So you have -1 plus -1 plus -1 plus 0. So that's -3 times n. All right, now use our little formula up here and replace each one of these entries. And so we have that n times that Laplacian matrix, we have the sum of the eigenvalues times these entries here. Well, now, if you look, it factors nicely. So we really get, it's a sum of the eigenvalues times h, the kth column uth value, kth column wth value, times kth column vth entry, kth column x entry. All right. And if you look, there's 3 shaded boxes. Let's talk about all 3. The first shaded box is your eigenvalues. But we know from a previous result, our eigenvalues are even. So lambda k, even number. Now the other 2 shaded boxes are sums of 1s and -1. So it's either 1 plus 1, which is 2, 1 minus 1, which is 0, or -1 and -1, which is -2. So those are also even as well. So you have an even times an even times an even, which means this is divisible by 8. All right, so 8 has to divide the right-hand side. But that means 8 has to divide the left-hand side. And look at what's on the left-hand side, 3 times n. Well, 8 doesn't go into 3 at all, and 8 can't divide n, because our assumption we haven't used yet is that n looks like 8k plus 4. Impossible. Done. And that's why there's only those 2 connected graphs, and then the complements bring us up to 4. So that's it. That's the whole proof. All right. Nice proof. Okay, well, now on to the other part. So we know how to handle 8k plus 4. Now what about the rest? So now we're going to start moving towards our computation. And the first thing is to say, well, we can assume that our Hadamard matrix is normalized. And that says the first row and first columns are all 1. So our Hadamard matrix has essentially, it's bordered, there's a smaller h hat, which is a ±1 matrix. That has some nice properties we'll get into. So now say, okay, great. We know that our Laplacian matrix it looks like 1 over n h lambda h star. And so what can we say? Well, it says that the entries of the diagonal entries on the first row, and of course highlighted there to emphasize that, of the Laplacian are determined by lambda. So if we know what the eigenvalues are, we know what the first row is, because we assume we have the matrix. Now, why do we care about the first row? Well, we like the first row because if you think about it, it's off diagonal. So we don't include, the entries on the off diagonal are either 0 or -1. So that pattern of 0 and -1 is determined by our spectrum. Okay, and that's not too hard to figure out. In fact, the computation is shown here on the screen. So if you multiply the eigenvalues by this appropriate matrix, you get your entries here in the Laplacian matrix. All right, well, what can we do? Well, what we can do is it turns out that this matrix H hat is invertible. And in fact, 1 over n H hat has a really lovely inverse. It's our H hat transpose subtract J. All right, so now what does that tell us? Well, it tells us that the eigenvalues can be determined by the first row. So we were saying, hey, the first row can be determined by the eigenvalues, but we can flip it around and say, if we know the first row, we know what the eigenvalues have to be. But if we know what the eigenvalues are, we know the whole matrix. And so what we can come to the conclusion of is once we look at the first row, if we know what the first row is, it forces the whole rest of the matrix. And so, well, how many possibilities are there? There's only 2 possible entries for each entry on that first row, because we ignore the diagonal entry, 0 or -1. And so that only gives us 2 to the n-1 possibilities to check. Now, there's a little caveat here. And the caveat is you can specify the first row to be 0 and -1 along there in some way. It doesn't guarantee that all the rest of the entries are going to be 0 and -1 in the off diagonal. So that's why we have to do a check. And but the good news is that's exponential. So that's somewhat reasonable, more reasonable. All right, now there's a nice little bonus that we get. And this shows that all eigenvalues are even integers. And the way we get the bonus is to say, look at what can we say about the entries of this H hat star minus J. Well, remember, this is a part of the Hadamard matrix. So originally just the H hat is 1 minus 1, subtract J, and then we get 0 and -2. So we have a matrix which has entries in 0, -2 times a column in 0, -1, which means that when we add everything up, each of these lambda i's are sums of 0s and 2s. And so they have to be even integers. And so that's a nice little thing that we get out of this approach. All right, so that's the basic idea. Specify the first row and then look through all possibilities. Now, to get a little bit more detailed here, let's talk about how we actually go through it. And so we did a little bit of tree exploration and did a little bit of pruning to help speed it up as well. Now, there's a lot of stuff on the screen here, so I just want to explain what this you're seeing here is. So there are 15 columns, and what you should really think of here is that each column corresponds with an entry on that first row. So in other words, I'm looking at, there's a 0 or -1, 0 or -1, 0 -1, and so forth and so on. And now what you see for the rest is you're saying, well, how do I figure out an entry in my matrix as a linear combination coming from my first row? Because that's one of the things that we're basically saying. If you go back to the previous idea, we said that everything is a linear combination of what happened in the first row. And so, for instance, here we see that we have a half, that would correspond to 1, 2, 3, 4, 5. So the 6th entry in the first row, the 7th entry in the first row, the 14th and the 15th. And so depending upon whether you have -1 or 0, you take the appropriate combination, and then that entry will be whatever it turns out to be. We want it to be 0 or -1. And so that's why we can do a little bit of pruning. And the way we do it, if we're going to be smart about it, is we say, okay, well, let's do a little bit of a pre-sort of the columns, because we can. So it's the same columns. All I've done is I've sorted it in a nice way. And I start saying, okay, I'm either going to make the first entry 0 or -1. The second entry 0 or -1, the third 0 or -1, the fourth 0 or -1. Now, suppose I had said, oh, well, let's suppose I have the first 3 entries be -1, and that one be a 0. You have a -1/2, -1/2, -1/2. So you currently have -3/2. And then you got into here, and then the rest of that row will not change that entry anymore. And so regardless of how you specify the 0, -1 pattern for the rest of the first row, if you have -1, -1, -1, 0 for the first 4, you can't get to a 0 or -1. So that's why we say, look, we can chop the tree off and save ourselves some time. And that helps speed up computations. I will say, of course, the biggest speed up to computations is having a good programmer. And so Bernard Lidický is a very good programmer. And we got the code was originally written in Sage, which is a wonderful way to explore. And we made it super efficient. And after we had optimized it as far as we could in Sage, Bernard took it and in a couple hours made it 1,000 times faster by going into C. But there's things that we were able to do. We were able to get everything to work in integer operations. And so there's no fractions that needed to be involved. The whole code, by the way, is online and you can download it. It's pretty simple once you understand the idea. And of course, the other thing to speed it up is it's nice to have a little sort of computational cluster available to you. And so Bernard, he had some friends in the Czech Republic, and he was able to borrow some computer time for a couple of weeks to run it. And so that's how we did a lot of our computations for larger sizes. All right, so what are the results? So that's the idea, right? We specify the first row, we check to see what the rest of the rows are, and if they're all zeros or -1s in the rest, we have a graph. There's our graph, and we just run through all possibilities. So for 16, there are 5 different Hadamard matrices up to equivalence. And if you look at where these are, the names come from Neil Sloan's. He has a website about Hadamard matrices. And so the had.16.0, that's the Sylvester construction. That's the one that gave us 46. So we know what those 46 are. And it turned out that all 5 of these different Hadamard matrices had a different set of Hadamard diagonalizable graphs that were associated with them. Now, they were all nice graphs. Essentially, we ended up with 4 extras. And you'll notice that the had.16.1, whatever that one came from, actually has all of them. So it's sort of universal, gathers all the ones for 16. You might say, okay, well, where are the other 4? Well, one of them is the Strikhandi graph. And then its complement, because complements are close. The other one is essentially the Strikhandi graph again, plus a nice matching, and then its complement. So those are where the other 4 are coming from. If you recall, we said that for the Sylvester construction, everything came from a graph, which was a Cayley graph in Z2 to the 4. And the other 4, they come from Z4 to the 2. So that's where the rest of them come from. And so that's it. And if you want to see the explicit graphs, you can go, it's in the full paper. We write out what all the graphs are. But really the big news is the Strikhandi graphs and how it breaks up. So obviously some graphs do much better than others. Okay, so that was for 16. 20 we don't need to do because we already know that's 4. So the next one is 24. Okay, well, for that, turns out that there are 26 possible. And different Hadamard diagonalizable graphs. And again, what we can do is we can take those graphs and we can break them up into families. And there's, in particular, there's 4 families. And then depending upon which matrix you have, you get different possibilities. So for example, there's one Hadamard matrix of order 24, which only has 4 different graphs that it can diagonalize. And we know that it has to do at least 4. So in some sense, it's a very bad Hadamard matrix. There's 7 of them that construct all of them. And there's one of them that has this unique sort of like family of graphs associated with it. And then there's a lot of them that have A and B. Now, some examples of graphs in these different families: the complete graph is inside of A, which is no surprise because the complete graph is always Hadamard diagonalizable. 4 copies of K6 is an example of a graph inside of B. A Cartesian product of K2 and K12. So think of it as you have a K12, and then you just have edges going straight down. And that's an example of something inside of C. And then similar, a K2 Cartesian product K66 is an example of what's inside of D. And so you can look at all of these. They're all interesting in some sense, because they now have a nice property. They're all Hadamard diagonalizable. But there's one which I think is really interesting. And I thought, I was like, wow, this is cool. Okay, and that's the cocktail party graph. But namely 2 copies of the cocktail party graph on 12 vertices. Now, if you recall, what is that graph? Well, that's the graph where you can imagine the reason they call it the cocktail party graph is you have 6 couples. So a total of 12 people go to a party. And then when you're at the party, you shake the hand of everyone you meet, but of course you don't shake the hand of the person you came with. What's the resulting graph? Another way to think about it is you take a complete graph and you subtract a perfect matching. So that's what we have. And it turns out that one of these graphs that's Hadamard diagonalizable for order 24 is 2 copies of the cocktail party graphs on 12 vertices. And the reason I find that fascinating is just one copy by itself, which is a graph on 12 vertices, is not Hadamard diagonalizable because there's only 4 graphs which are Hadamard diagonalizable for order 12. And it's not one of those 4. So the fact that by itself it's not, but when you have 2 copies of it, it is. It's very strange, at least to me. Okay. Well, I see we're going at a good pace here. So, 28, no surprises. 32, might take us a while here. There's a lot of graphs. And so we're not going to discuss all of them. So there's 10,196 different graphs, which were Hadamard diagonalizable. Now, there's also a lot of Hadamard matrices, 13.7 million. And what we were doing before with the different Hadamard matrices is we were sort of grouping them together by saying, well, what graphs can you diagonalize? So there were sort of equivalence classes. So what you do is you say 2 matrices, Hadamard matrices, are equivalent if they diagonalize the same set of graphs. And now, if you do that for n equals 32, we end up with a lot of different equivalence classes. So in particular, there's 53,420 different equivalence classes. So there's just this whole fracturing that goes on at 32. And so what you're seeing here is you're seeing just sort of an idea of some distributions. So on the vertical axis, it's how many graphs you diagonalize if you're in your particular equivalence class. On the horizontal axis is how many matrices are in that equivalence class. And it's in log scale. And so you'll see 10 to the 0 means, hey, there's only one matrix that diagonalizes this particular set of graphs. There's actually a fairly significant number of different equivalence classes which just have one matrix. And you might notice way far out, there's a dot on that side. And that dot if you look at it, that's 10 to the 7th, 10 million. That's a lot of graphs. And that's a lot of matrices, and a lot of matrices which only correspond with 10 to the 1 graphs. Okay, so we won't go through and do case by case for each graph, but we'll make some comments here. So some comments, and just a footnote. I mentioned the code is available, and so is the output. So we have output that says, here's that Hadamard matrix. Here are the graphs associated with it for all of them. And if you say, look, I don't care about the actual Hadamard matrix that goes with it, I just want the graph. We have the graphs in graph 6 string available as well. Okay, so the first thing was that dot I was pointing to. So there is an equivalence class which has over 10 million of the Hadamard matrices, which means if you just randomly pick a Hadamard matrix of order 32, very likely you're in this equivalence class. And there's only 10 Hadamard diagonalizable graphs for those matrices. So if you just start randomly picking matrices and start to try to find, oh, interesting graphs, well, it might take you a while because most matrices don't have very many. There are 29,270 matrices which only have 4 Hadamard diagonalizable graphs. And remember, everything always has at least 4. So even at order 32, you can come up with matrices which aren't very good at forming these graphs. There are 26,064 of these equivalence classes with just a single matrix. That's that first vertical column. And so there's in some sense, that's almost half of the equivalence classes that are uniquely determined by the set of graphs. Now, there's also 966 different Hadamard diagonalizable graphs which have a unique matrix which diagonalizes them. And in other words, they're just sort of like barely diagonalizable. You have to get just the right Hadamard matrix, otherwise you won't find it. So it's like searching for a needle in a haystack, which is why it helps to be exhaustive. Now there's 13 such matrices that have a unique, are that unique matrix. And so anything else? Here we go. And of course, once you have it, you can start doing some statistics. So here, nu of G is the clique number. So you can say, okay, what's the size of the largest clique? And so, for example, there's one graph where the largest clique is 32. Well, that's not too surprising, the complete graph on 32. There's also one graph where the largest clique is 9. Okay, well, that maybe is a little bit surprising. I don't know if you would think that there's only one of them. And okay, you can get some interesting distributions here of various statistics. You can do all sorts of statistics because you have the graphs, and you can start saying, what are some nice things about them? And what are some nice spectral things, for example? I'm somebody who, I like spectral things. Well, okay, that's some general comments. Maybe we should look at some examples. Okay, so here's an example. So what we see here is one of our Hadamard matrices of order 32. You should think of it as a white square corresponds to a 1, and a black square corresponds to a -1. And so there's our nice Hadamard matrix of order 32. You might say, okay, great, there's one. What's special about this one? Well, this is in some sense the powerhouse, because this has over 3,000 different graphs which are Hadamard diagonalizable by that matrix. And so there's some beautiful structure going on with that matrix. And not only are there 3,000 different graphs, 92 graphs can only be diagonalized by this particular matrix. So this is a very interesting Hadamard matrix. On the other hand, we see another one. Here's another Hadamard matrix, again, order 32. And this one, well, it's slightly smaller in terms of the number of different graphs, 1,600. But this one, wow, 224 graphs are only diagonalized by this Hadamard matrix. It's if you're looking for like, what's a really unique kind of graph, this one has a lot of them. All right, well, what's another one? And like, okay, well, here's another Hadamard matrix. And this one only has those basic 4. And you're like, wow, okay. That seems a little bit more noisy than the rest, but all right, what's going on? Why? What's some reasons here? Now, at this point, you might be thinking, wait a second, there's 13 million Hadamard matrices. We've only seen 3. We have 13 million more slides to go? No. These are just some examples. And so again, there's plenty of room to explore. All right, well, I see I'm going pretty quickly here. That's all right. Some remarks here. Well, what are some interesting constructions that show up in our Hadamard diagonalizable graphs? Now, before you hit order 32, everything's a fairly nice graph in the sense it can be a Cayley graph. At order 32, most of them are no longer Cayley. And so you've lost something. So something's happened at order 32. But there's still some nice structures. Now, you can ask a question about the matrices. You say, okay, what makes some Hadamard matrices have many Hadamard diagonalizable graphs and others have relatively few? And I have no idea. But the nice thing is you can always say like, well, I think this should be an interesting Hadamard matrix. You can find out how many graphs it does. And all right, what about interesting spectral properties can we find? Now for order 32, the most common spectrum was the following, where you had 1 eigenvalue of 0, 6 eigenvalues of 12, 15 eigenvalues of 16, and 10 eigenvalues of 20. And that corresponded to, there were 528 non-isomorphic Hadamard diagonalizable graphs with that spectrum. All right, well, of course, there's lots of different spectrums. They're pretty clean. What are some things we can say about these? Now, something that might interest people in this seminar, what about perfect state transfer? Because this is like strong candidates. You've got your plus minus 1 eigenvectors. You got really clean eigenvalues. Here you have 10,000 new candidates. How many of them have perfect state transfer? Okay, well, it can be found out. And I would add that if you want to pursue this, it doesn't take much to modify the code to not only have the Hadamard matrix input and say, oh, here's the graph, but actually says, okay, here are the specific eigenvalues and eigenvectors that go with that graph. So if you're interested in it, it can be done. What about larger order? Now, for example, 40, 48, 56. And you might start to wonder, can the computer handle it? And the answer is yes. We actually were able to run the 40, 48, 56 Hadamard matrices that were in Niels Sloan's Hadamard index. For those, we don't know what all of them are, and Niels Sloan seemed to be biased towards ones that had a really beautiful pattern, which don't seem to produce very many. And so there's a fairly small number there. When we plugged in for 48, we just did Sage has a way to say, oh, here's a Hadamard matrix for order 48. When we plugged that in, we got a couple hundred different Hadamard diagonalizable graphs. So we do have the computational power to handle them. The only issue is we don't have the exhaustive list. If we had the exhaustive list, we could have done them. But certainly if you say, oh, I think I have a really interesting matrix for a slightly higher order, say, let's keep below 64 for now, the program can handle it. Now, I will say, on very flimsy data, like I said, we did run the Hadamard matrices through. And so remember, we had this nice, beautiful result that said, if you're 8K plus 4, there's exactly 4 and only 4. And for 16K plus 8, we looked at the data that we can produce. And we know, for example, for 24, we know the answer is there's only 26, and they're all very nice. But when we ran it in the larger cases, for example, for 40 and for 56, we again saw 26 from the ones from Neil Sloan. And so it might be the case that for 16K plus 8, there is at most 26 Hadamard diagonalizable graphs. So that is a maybe better posed as a question than a conjecture, because again, we don't have the greatest evidence for it, but I suspect something might be true. If it is true, you probably cannot push it any further, because like we said, at 32, just things go crazy. You know, we lose the nice constructions because most graphs are no longer Cayley. But I want to be optimistic and say you might be able to push it just a little bit more. All right, and with that, thank you. And that's what I wanted to talk about.
Thank you, Steve.
Any questions?
Yes, you can just unmute yourself.
Thanks to you. Was it me? Sorry, Tina.
Yeah.
All right.
Go ahead.
Steve, there's you had this observation that the union of two copies of cocktail party graphs and two vertices is Hadamard diagonalizable, but not the single copy, right?
That is correct.
Is there a characterization of such graphs?
Not that I know of. I mean, that was because I was interested in this because I was looking at 32. And so for 32, I was like, okay, is it possible that we have some interesting things going on? Because if you have, say, two copies of the same graph on order 16, which is Hadamard diagonalizable, you're going to be Hadamard diagonalizable again.
Right.
And so I started going through, and I was like, oh, wait a second, there's like one extra here that doesn't seem to belong. And I finally figured out what was happening was, it turns out that for order 32, there are two different Hadamard diagonalizable graphs of order 16. So they're distinct, where their union is Hadamard diagonalizable for order 32. So you have, that's something that's, you know, it's definitely not Cayley, because you have two different graphs, disjoint union of them together. So I don't know off the top of my head which two they were, but that one was like, wow, that's weird. But generally speaking, that just sort of seemed to be like the big exception. And I don't have a good explanation for why that should be true.
Right.
It seems to me the more intuitive thing says, oh, if you have a disjoint union of graphs, they both should be Hadamard diagonalizable. But that's not true.
Thank you.
Okay, I see Ada has a question.
Yeah, thank you for a very interesting talk. So I have a question about that same example. So which Hadamard graph, Hadamard matrix is this? I would like to play with that example a bit more.
For you're talking like the
cocktail party graph, the disjoint union of the K2 bunch of
right.
two. Yeah.
Let's see if
That's
I can
size 24.
I got too excited. I went way too far back. Okay.
Yeah,
Well, definitely if you go with anything in the first 7. So if you go to Neil Sloan's list,
yeah.
and so you have the Hadamard.24,
Right,
anything in the first 7 definitely includes it, because they have everything.
Yes, you're right. Okay, thank you. And my other question is, I think this is for size 32, and you mentioned the 13 matrices, each has exactly 966 graphs that they diagonalize.
Let's see. There are
the fourth bulletin point.
Yeah. So I would say that. So there's 966. So let me be careful how I phrase this. So there's 966 different graphs.
Yeah.
Which can only be diagonalized by one Hadamard matrix.
Right.
But it's possible that a Hadamard matrix may diagonalize more than one of those. So it turns out that even though there's 966 different graphs, which only have one matrix, they all belong to a family of 13 matrices. So there's 13 matrices which combined cover those. And if you go to the example on the next slide, where
I see.
this one, you see, oh, there's a lot of graphs which are only diagonalized by this one. So that's why, you know, you don't need, like, even though there's 966 different graphs, you don't need 966 different matrices. You only end up needing 13. So, you know, there's one question I didn't answer, which I probably should have, because we have the data, is like, okay, suppose you wanted to come up with just like a nice set of Hadamard matrices, which collectively you diagonalized everything. Well, the answer is we need at least those 13, because each one of those 13 has like a unique representative. But I don't think that's enough. And I don't know what the smallest number is.
Can I ask one more question?
Sure.
Okay, so have you looked at what happens if let's say I have two Hadamard matrices, and let's say the equivalent. Okay, I'm thinking it from the numerical algebra point. And so I want to find the graphs that are diagonalizable by those two, or even n of them. So I'm just thinking about, so I start with a normalized Hadamard matrix, but then I can normalize each column and end up with n different normalized Hadamard matrix.
Right.
And the numerical algebra is the set of graphs that are diagonalizable by all these n matrix. So with your method, do you think it can be extended to finding these, doing such a computation? Or?
So we have a question in the paper. So we actually ran the computation, because we, you know, there's certain things that don't matter, like permuting the rows. Okay, that doesn't matter. It's just relabeling the vertices. Permuting the columns, okay, that doesn't really matter. Up to the first column, you know, there's things that didn't matter. And we said, well, because you bring up a good point, which I'm kind of like, didn't talk about. You know, you're exposing us, but that's okay. Which is, okay, so there is something which can't automatically, you know, be fixed, which is, all right, what if I flip the first and the sixth column and make the first column all ones, which you can do, and it's equivalent. So we ran the computations where we actually did that for each matrix. We went through and made each column, moved it to the first, and did the computation. So we know we did exhaustively check everything. And I think so Bernard was the one who had his, you know, friends in the Czech Republic. If I recall the code, I know for smaller orders, the following is true, and I think it's true for 32. It didn't make a difference which column you picked. So changing which column was the first column did not have an effect on which Hadamard diagonalizable graphs came out. I know that's true for below 32. I think it's also true for 32, but I can't remember exactly the code, whether or not it checked that as part of it. For 32, we were definitely checking whether we missed anything. And there were several times where it feels like we were really close to a proof, but we couldn't quite get it there. So I do believe that if you do have a Hadamard matrix and anything that's equivalent under the traditional definition of equivalency for Hadamard matrices, then you will only have a certain set of graphs. You can't change it. And that's a conjecture, but that one I believe.
Hi, I had a question regarding, like, how do you determine whether a Hadamard diagonalizable graph is Cayley graph?
There are certain things you can run in. So I think Sage has a built-in is it Cayley command, which is very inefficient, if I recall, and I hope it's accurate. One of the things that I discovered by doing this was that, at least on the version of Sage that we were using, which may be a little bit outdated now, there's the there's the canonical label commands, and there's the graph 6 string commands. And so canonical label, in theory, makes a canonical labeling, but we could tell by the output that it wasn't actually canonically labeling things. So that there are some graphs which it couldn't canonically label correctly. And the reason we could tell by the output was we had an odd number of graphs coming out. But remember, things always come in pairs. And so you can't have an odd number of graphs coming out. The good thing is that when Bernard ran his program, he went back to the, I think the real source code for C. And so I think it was a pure implementation of canonical label. And then we no longer had the, hey, there's an odd number of graphs here. Well, isn't that kind of weird? So.
A couple of comments. Even in Sage, you can access the naughty routines. And so there's you can use the naughty canonical label and that will be fine. And the second comment is that Gordon Royal has for example, has all the cube-like graphs on 32 vertices. And so you can do things backwards. They're all Hadamard diagonalizable, and they're all the ones that are calligraphs. And so anything that's not on that list is not a calligraph.
Well, it's not a calligraph for Z2 to the D.
Yeah, okay. Well, okay, but you can get the other ones too. I mean, I've worked really carefully here, but
sure.
Yeah, yeah. So it's going to get fancy if you start saying it might be a calligraph for a non-abelian group. Avoid it to 32 and then you're in trouble.